Okay, so welcome to this video. In this video I'm going to introduce the Galois Theory, and its use to solve polynomial equations. Okay, so firstly, we're not going to actually use it to solve a polynomial equation. We're going to use it to solve a much more simple algebraic problem. So I'm going to just sort of outline what it actually is in a way that's actually understandable, because the usual courses that we've done this will tell you the fundamental theorem of Galois theory and all of this, and I don't think that's particularly helpful for a beginner. It's something that you need to look back over once you actually understand the basic concept. So the way I like to view what Galois theory is when we have, say, a polynomial, let's say, for an simple example, we're using field algebra now. We're using the common algebra, the one that you all learn in school. So where we have addition and multiplication, and they obey the usual rules. So if we have the polynomial, say x squared plus 1, and we're looking for solutions, we know that the two solutions are x is equal to I and x is equal to minus I. And you might remember from secondary school, or from A-level maybe, that there's a link between these two solutions that's very obvious here, that one is the complex conjugate of the other. So if you put a negative sign in front of one, you'll get the other. So you can take one root and map it onto another root with this law. And the law for transformation is complex conjugation. So if you complex conjugate one of your solutions to the equation, if it will always map it onto another solution of the equation, and that's always true, providing the coefficients of this polynomial are are rational numbers or real numbers, or as long as they're not complex numbers, as long as they don't have an imaginary part, then it will always be true that complex conjugation of a root of the polynomial will map the root onto another root. And that's still true even if we take a polynomial like x squared minus 1 is equal to 0. Here the solutions are x equals minus 1 and x is equal to 1. Now take one of these solutions and take its complex conjugate, and what does it map it onto? It maps it onto minus 1, and 1 is mapped onto 1. And those are still solutions to the equation. It's useless. It's not giving you a new solution, but it still maps it onto a root onto a root. And that's a very important concept. Okay, so Galois theory is it's about this. It's about how you take one solution and you can map it onto another solution. And here one of the transformations is complex conjugation. Galois theory is about asking, if we say have a quartic or a quintic or some higher degree polynomial, and we've got however many roots, are there links, are there other transformations besides complex conjugation that will also map you onto another root? And it turns out there are, and we're going to examine these transformations in a very, very simple case for group algebra. So we're not going to do field algebra here, we're going to do a group algebra. We're going to use Z mod 4 as our group algebra, so the cyclic group on 4 elements. So remember, the cyclic group consists of an underlying set of 4 elements, so we've got 0, 1, 2 and 3, and it's got a Cayley table as well, so we'll draw out the composition table: 0, 1, 2, 3, 0, 1, 2, 3. So 0 added to 0 modulo 4 is still 0. 0 is the additive identity, so it's the identity in this group. 1 composed with 1 is 2, 1 composed with 3 is 3, 1 composed with 3 is 0, 1 composed with 2 is 3, 2 composed with 2 is 0, 3 composed with 2 is 1, 0, 1, 2. Okay, so there's our composition table for our group. And now what we want to ask, so firstly, just for a bit of a warm-up, let's have a look. Remember, groups are the simplest structures we can actually solve simple equations in. So instead of calling this addition, I'm just going to call it abstract composition. So this is the composition symbol. So we've got Z mod 4 under the composition. Okay, so say I had an equation like this: some unknown element of the set composed with, let's say, 1 is equal to 3. And I want to solve that equation. The way that you do it is you compose on the right with 1's inverse element. We don't know what that is yet, but we can work that out. 1's inverse. And then these two here will automatically give the identity, so they will give 0. So x is equal to 3 composed with 1's inverse. So we just need to work out what is 1's inverse. So we need an element such that when it composes with 1 composed with 1 inverse has to give the additive identity. So 1 composed with something has to give the additive identity. Well, that's 3. The only thing that composes with 1 to give the additive identity is 3. So 1 composed with 3 is equal to 0, so 1 inverse is 3. So what we need to do is we need to compose 3 with 3, and when we do that we get 2. So the solution is 2. So x is equal to 2 is the solution. Oh, well, you can't see this. X is equal to 2 is the solution to this equation. In the next video, what we'll do is we will consider the solutions to this equation. X composed with x is equal to 2. Because this is a bit more of an advanced equation now. We've got the unknown composed with the unknown is equal to 2.